The following theorem summarizes the various possibilities for limits of power function when x increase or decrease without bound. So, if p is a positive real number and q is any real number except 0, which is different than 0, then first fact, limit when x goes to minus infinity, q over x to power p equals 0. And second one, limit of the function q over x to power p when x goes infinity is also 0. Third one, limit of the function q times x to power p when x goes minus infinity is either infinity or minus infinity. And the fourth one is limit when x goes to infinity, q times x to power p equals infinity or minus infinity. Maybe some people can say that it is not possible to be minus infinity, but according to the sign of the key, sometimes it can be minus infinity. For example, minus x square. So, these four equality hold provided that x to power p is a real number for negative values of x. The limit in third and the fourth will be either minus infinity or infinity depending on the number k and p. Okay, so for example here k is positive, p is all even number, this is always positive. If k is positive, p is odd number, this is negative, minus infinity. If k is negative, p is even number, again this is minus infinity, etc. Okay, we have some variety here. How we can use this theorem to evaluate the limit at infinity? On the example in the lecture, in class lecture, I will explain because we need some observation to decide which limit correct for the which functions. Now we can talk about the limits of polynomial function at infinity. So as a theorem, let's write again. If the polynomial px is the following form, plus am minus 1 x to power m minus 1 plus blah 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 plus a1x plus a0. Here an, it is leading coefficient, is different than 0 for n bigger than and n bigger than equal than 1. Then limit of p of x as x approach infinity equals limit x goes infinity an x to power n. I don't like this formula actually, but in your textbook it is given as a theorem. Briefly, I can say that the behavior of this polynomial is similar to this function at the plus infinity and at the minus infinity. So according to the an is like the key and n like the p. So according to key and the p, this limit is either infinity or minus infinity. Okay. So generally I omitted this part. So according to the leading coefficient and the leading term, maybe completely we can say leading term, we can decide this is infinity or minus infinity. And similarly, limit of p of x as x approach minus infinity equals limit x approach minus infinity an times x to power n. Okay, this one. So this limit either equals plus infinity or minus infinity again, okay? Each limit will be either minus infinity or infinity, briefly, depending on the leading coefficient an and the power, highest degree power n. According to these two limit, we can say that polynomial function does not have any horizontal asymptote. Okay, actually before we said this one, so I'm repeated here. So how we can find the horizontal asymptote? Actually, for the rational function, we have a strategy. So finding horizontal asymptotes. Since a rational function is the ratio of two polynomials, it is not surprising that reciprocals of power of x can be used to analyze limit of the rational function at infinity. For example, let's consider this example. 5x cubed minus 4x squared plus x minus 1 over minus 4x cubed plus 2x squared minus x plus 4, for example, okay? Let's consider this rational function. So the limit of this rational function can be calculated as the following form. First, we consider this rational function as the following form by taking 5 x squared common factor x cube common factor parenthesis. Here 1 minus 4 over 5x plus 1 over 5x squared minus 1 over 5x cube. For the denominator, by taking 4x to power cube parenthesis, 1 minus 2 over 4x, so which is 1 over 2x plus 1 over 4x squared and minus 1 over x cube. So when x goes to infinity, this terms goes to 0, this terms goes to 0, this terms goes to 0, and that goes 0, this goes 0, this goes 0, as x goes to infinity or minus infinity. So we can say that limit when x goes to infinity f of x equals limit when x goes to infinity 5x cube over minus 4x cube. And here x cube terms cancelled. Actually there are infinity over infinity term form, but here you can cancel because x goes to infinity for both case. So this limit equals equals 5 over minus 4 or minus 5 over 4. And similarly, you can calculate the limit x goes to minus infinity f of x equals limit x goes to infinity 5x cube over minus 4x cube, and a times limit of the rest part x goes to minus infinity, so rest part is 1 minus 4 over 5x plus 1 over 5x squared minus 1 over 5x cube over 1 minus 1 over 2x plus 1 over 4x squared minus 1 over x cube. And again, all this term goes to 0, this goes 0, this goes 0, this goes 0 when x goes to minus infinity. We obtain this result. So as a result, this limit equals minus 5 over minus 4. So minus 5 over 4 again. So this two limit implies y equals minus 5 over 4 is a horizontal asymptote for the function. Briefly, as a theorem, we can give the following fact for the rational function. First part, if f of x as the following form rational function x to power m plus a m minus 1 x to power m minus 1 plus blah 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 a1x plus a0 over denominator is b sub n x to power n plus b sub n minus 1 x to power n minus 1 plus blah 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 b1x plus b0. Here am and bn leading coefficients, so which are different than 0, okay? So am different than 0, bn different than 0, then limit x goes infinity f of x equals limit x goes infinity am x to power m bn x to power n, like the my previous explanation, okay, like this explanation, and limit when x goes to minus infinity f of x equals limit x goes to minus infinity a sub m x to power m over b sub n x to power n. So according to this limit, we can say that as a second part of this theorem, there are three possible cases of these limits, okay? First case is if m less than n, the degree of the numerator is less than the degree of the denominator. So in this case, limit when x goes to infinity f of x equals limit of the function f of x as x goes to minus infinity. These are equals 0. And this implies y equals 0 is a horizontal asymptote. The second case, if m equal n, the ratio of the leading coefficient of the numerator and denominator will be our limit, like our previous example. Limit of the f of x as x approach infinity and limit of f of x as x approach minus infinity equals am over bn. That means y equals am over bn is a horizontal asymptote. The third case is if m is bigger than n, the degree of numerator is bigger than n. So numerator is very, very big when compared to denominator. So that means each limit does not exist, goes to infinity or minus infinity. Then each limit will be plus infinity or minus infinity, of course depending on leading coefficient and the degree of the polynomial m, n, am and bn. Depending on these four values, this is infinity or minus infinity, and f of x does not have a horizontal asymptote in this case. So please note that from the first and second part of here, from the second part of this theorem, the limit is the same if x approach infinity or minus infinity. Here 0, here am over bn. If x approach infinity or minus infinity. So a rational function can have at most one horizontal asymptote. It may not have any asymptote according to third case, but according to first and second case, a rational function can have at most one horizontal asymptote.